everyone, and welcome to this Caterpillar Webcast, Combined Heat and Power with Reciprocating Engine Generators, Cost-Effective and Clean Energy. I'm the moderator, Nick Kelch. I work with Caterpillar Electric Power Division. I've been with Caterpillar for the past 12 years and am currently part of Caterpillar's Electric Power Business Development team. Also on the line today, we have with us some of my teammates, Tim Scott and Diego Matra, also of Caterpillar's Electric Power Business Development team. We have a cumulative of about 70 years of experience here on the phone supporting the webcast. Before I get into today's subject matter and introduction of our speaker today, a couple housekeeping items. We'll have about a 45 to 50-minute presentation. We've reserved 10 minutes at the end of the session to answer some of your questions live at the end of the webcast. You'll notice your presentation console here has several different applications. The app labeled Q&A is for questions and answers. You can feel free to submit your questions to us throughout the webcast. We'll try to respond to all questions, either directly by responding to your text. You can refresh your text window to see those responses. If we're unable to answer your question, we'll be sure to follow up after the webcast with an email to you directly, if not live on the webcast. We appreciate your attendance today. You'll also note on the console we have a few other apps where you can find links to our online community, newsfeed, cat.com pages, as well as our Facebook page, should you be interested. You'll also note that we'll be providing a recorded version of this webcast. It will be available for 3 months after the event. You could use the same link you used today to come visit, or you'll be reminded with an email after the fact when that recorded version of the webcast is live and viewable. For those of you who have registered to receive a continuous education credit for your professional certifications for your attendance today, we will be emailing those out to you within a couple weeks at the conclusion of the webcast. So please stay tuned with us. And at the end of the webcast, we have a couple questions for you where you'll be answering and providing us with feedback. We do ask that you do stick around to the end and provide that feedback to us. But without further ado, I'd like to introduce our speaker and get to topic here. Francois Xavier Sori is a cogeneration and electrical systems application specialist responsible for Caterpillar's electric power business development in cogeneration and combined heat and power systems. Francois Xavier has over 17 years of experience in the power generation industry, leading project development of gas and diesel-fueled engine power plants, turbine power plants, CHP, and electrical systems. He joined Caterpillar in 2003, and for the last 7 years has worked as territory manager for Africa and the Middle East. Francois is a certified Six Sigma Black Belt and has the position today of Electric Power Business Development Manager, supporting cogeneration projects globally. Francois Xavier has a postgraduate degree in electrical systems engineering from the University of Essex. And without further ado, or actually before I do pass presentation responsibilities off to Francois, I'd like you to share with us some quick poll questions, and I'll share the results with the entire audience so that you can get a feel for who's joining you today and we can get a feel for the level of interest. If you could please submit your answer to this question: where do you reside? Let's see, I do believe we have a fairly global audience joining us today, but let's find out for sure, and let's see your responses here to this question. Our results, you can see we have a primarily North American audience today, some European, as well as some Asia-Pacific, Middle East, and Russia CIS folks joining us. So indeed a truly global audience. Interesting. We'll take note of that. Another question that we're curious to ask you, engage your interest and level of understanding, and do you believe that cogeneration today delivers secure, affordable, and sustainable energy? Maybe you're not sure, maybe you're here to learn, but if you could go ahead and share your brief thoughts on this topic with us, and I'll give you a second to respond, and we'll share the results with our audience. Looks like a majority either believe so or not sure. Perhaps it depends on the circumstances. That's interesting. And then finally, a brief question on your interest in the types of cogeneration that may apply to your industry. Which of the following cogeneration applications do you have the most interest in? Electricity and hot air, hot water, steam, chilled water, desalination, perhaps carbon dioxide recycling. You can select multiple answers here. Let us know what your interest level is, and I'll go ahead once again, and if you want to answer, I'll share the results from this poll as well. Looks like, again, quite a diverse interest, including carbon dioxide, pretty much everything. And that's good news because we're going to talk about all these topics and other ones, perhaps, not included in this poll question throughout this webcast. So without further ado, I will go ahead and transfer presentation to Francois Xavier.
Nick, thanks very much. Good morning and good afternoon, everyone. It's a pleasure to introduce you Combined Heat and Power from Caterpillar today. Just a quick fact here. If you look at the way power could be generated and heat could be generated separately, and you run a bit of numbers, you could see that the total efficiency of such separate productions is around 60%. 60% is good, but is it good enough? So now if you would produce power and heat with the same cogeneration system, same CHP system, of course you see that the efficiency of that system will now be 80. And today we're going to look why this number is different and how can we even raise 80 further to the high 90s. And that's all about the presentation today. So cogeneration. Cogeneration is genset is the fuel that you put in and the power that you produce. That is a green arrow here in the center, and a lot of heat that is dispersed in the engine while it runs. This heat is here dispersed in different formats and different temperatures. And look at the exhaust, for instance. Exhaust is gas, and it's around 500 degrees C, about 900 degrees F. And how can we capture it? If you look at the other side of the arrow, you see also jacket water. Jacket water is water at 200 F, more or less, 190 degrees C. So the presentation today will be how can we capture and value on the top of the power the rest of the heat that is here at different formats. On the top of all this, it's nice. It's not just a good idea to build or to look at a CHP system. All of this is economically driven. All CHP plants are economically driven, and before you know you could be successful into implementing a CHP system, it's nice to look at some economics. And you will compare economics with the actual disparity between the CHP rates you will calculate and the utility rates. So to make a go or no-go analysis at a high level, these are the typical parameters we would need to collect. The price of the power you buy or maybe you sell, the cost of the fuel, the thermal credit, the cost of money, and the operation and maintenance. And these are typical numbers I gave you here. So this is very important. Once you know you're economical, look at the tactical. Is CHP a new concept? No, it's not. If you look at this slide, Caterpillar has been delivering CHP system globally since 1960, and I brought up this old brochure of ours that showed our old CHP system in the past. Today, the CHP system will look this way. This one is a 2 megawatt CHP recovery. You see in the front the water recovery from the jacket water and the aftercoolers, and here on the side of the genset you see the exhaust gas heat recovery. What is the most popular media people would like to recover the heat from a CHP? And the most popular media is hot water. Hot water is very useful in infrastructure, in industries, and commercial applications. So here you'll see how a customer will return water at 70 degrees C back to the CHP system that will take the heat first from the jacket water and then from the exhaust gas and brought this water back at 90 degrees C back to the customer and providing power, heat power, thermal power, and value to that customers. So this is probably the most popular, and I saw in the poll results that hot water was a bit of interest today. So let me show you how good hot water is used. Here is in France, hot water is used in district heating application. Caterpillar has over 800 megawatts installed in district heating CHP application in this country, and I'll have an example here. This is a nice 6 megawatt power plant built out of our 2 megawatts units or 3 units, and you can see a lot of pipes because these guys, they don't want to lose a watt, and they want to capture all the heat, and they have pipes and heat exchanger on all circuits they can find useful. Another example here is in Lithuania. In Lithuania, this was the first and largest CHP in Lithuania. It's a 2.2 megawatt with 2 units. Here is again a hot water heat recovery for district heating. This one is from Germany. And in Germany, we have numerous applications of that nature. Actually, we have 10 copies of this one at 10 different cities. And in that particular case, what is very nice in this application here for district heating as well is the very high efficiency, close to 90%. The 3-circuit heat recovery and a detachable module you can see in the front with the heat exchanger here in blue. This is the heat exchanger module from jacket water, aftercooler, and oil circuits of the genset. Here is another very nice example, probably the oldest CHP still running at the moment. It's about 30 years old. It's 200,000 hours of service, and it's located in North America, actually in a ski resort in Utah. And it's built out of 3 J399s, legacy old product from Caterpillar, still running. And you can see on YouTube, if you have time after this webcast, there is a nice video that explains how it works and how delighted the customer is. Here is some hot water recovery for industrial process. This is in the Gulf, in the Middle East, 6 megawatts for a chlorine factory in Oman, Sultanate. And Caterpillar provided these modules, the 6 megawatt power plant, plus the control system here. Still hot water for process. Here, a specific one, a different application, still hot water, but it's for a university, so it's more a community or a building heating. It's a 4 megawatt. It's the first CHP plant in Armenia. This was for the Yerevan University in Armenia. Again, hot water produced by the jacket water and the exhaust gas recovery. So once you have once you have hot water, what else can you do with hot water? The first thing that comes in mind, well, what about doing hot air? Hot air is useful.
Sorry about the technical difficulties, everyone. I'm going to go ahead. Oh, Francois is back. Sorry about that. Francois, please proceed.
So we've been at the hot air. So the hot air drying here. So once we have hot water and hot water being produced by the recovery from the jacket water and maybe the exhaust gas, hot water can be used to produce hot air. Here in this example that was used in Russia, we were able to produce from the outside air, in that example, 20C or 70F, a lot of air at 90 degrees C or 190 F at 140,000. I have to check because this phone is going on mute alone, so I need to check out. I will do that on a regular basis. All right, so here we go. Hot air is the way. We produce with hot water from the jacket water, and if you need really hot air, it happens on brick factory when you actually need very hot air temperature to dry bricks or ceramics. this is what we do. We use both the air generated from the hot water and the air generated from the exhaust. What else can we do on the top of? What else can we do on the top of hot water and hot air? It is steam, and steam can be generated with the exhaust gas of the generator only, and we can produce saturated steam, and saturated steam can be produced with the exhaust gas that is 860 F or 460. Then you can produce 8 to 15 bars, and this is enough to produce 1 ton of steam per electrical megawatt. And this is modest, but we can only use the exhaust gas to produce saturated steam at that pressure. All right. Now, if at the same time you want also hot water, in the combination you can produce hot water and steam together using the exhaust gas for steam and the jacket water for hot water. So 1 ton per hour for 1 megawatt. In some application, this might not be required. For instance, in food industry, there is need for steam at low pressure. And here, using our hot ebullient cooling Caterpillar genset, running with the jacket water temperature at 260 F, 127 C, we are capable to produce 700 kilograms per hour at 10 bar steam, and also 910 kilograms per hour of steam at 1 bar. So total of steam is now 1.6 ton instead of 1 ton. This is about 3,000 pounds per hour of steam, and this is very useful for food industry, for cooking and food processing and sterilization. This is very much done. This has been done here in Germany and in North Africa as well on a pasta company. So steam is important for the industry. Industry loves steam, and if you use the exhaust gas only, you get some issues or challenges with your efficiency. But if you use it this way, producing high pressure and low pressure steam together and a bit of hot water, you can raise efficiency here. This example is almost 89%. Here is an example of how a steam boiler from the waste heat recovery looks like. We normally position it next to the genset. Steam boilers are heavily instrumented, and these are different processes and different equipment than just hot water heat recoveries. So we want heat, and heat is very important, and we have a way to produce more heat than just heat. To do that, we incorporate in a traditional hot water heat recovery, we would incorporate a heat pump. Not a heat pump like the one you may have in your household, but an industrial, high-efficient heat pump. And this heat pump will use the energy that is in temperature that are normally too low to be recovered. You can see here on the central of the drawing, water at 25 degrees from the residual exhaust gases or the low aftercooler part of the equipment, and also the hot air from the room. Both, this heat pump will raise it to a useful temperature range that you can actually have a value for. So if you look in details, these typical heat pumps are popular here, especially in Europe. The coefficient of performance, COP, is very high. It's a screw type of heat pump. The electric power you need to feed that heat pump is 230 kilowatts here. But the beauty of the heat pump and the CHP is now you can raise the efficiency above 100%. Well, there is no magic here. 100% is on the LHV, and then since we condensate and take more heat than the LHV, it's 108%. So that's the beauty of using LHV or HV. The next slide is exactly the heat pump. This is a screw-type heat pump that has been used in Germany since 2004. It's COP 5.5, screw-type, very efficient, very robust. We've been running for now more than 7 years, and it's very good success for the customer, a lot of heat. More heat, more usage. What can you do with heat? A new application for you, it's desalination. Desalination can be obtained, fresh water can be obtained using the waste heat of a power plant. Here in this example, this application is well known because it's used on ocean-going vessels to produce fresh water on board the ships, and this is used here for stationary purposes. You can produce up to 12,000 cubic meter a day. In that particular case here, just to give you an example, if you give 7 megawatt thermal input to that system, low temperature desalt, you would get 500 cubic meter or 1,200,000 feet of fresh water per day. So this is the cheapest fresh water you can find if you can recover the heat from a power plant. Very cheap fresh water. More heat again, and we've used the heat from the genset to produce hot water. We used the heat from the genset to produce steam, fresh water. What else can we take from the genset? And here we go. What else is CO2? CO2 and heat recovery is very popular in greenhouses, and you see the complex heat recovery system to take all the kilowatts of heat from every circuit in the genset for the greenhouse. But in the middle of the chart here, you see a selective catalyst reductor, and this will actually clean the exhaust gas of the genset to a point that you can actually insert these gas when they're cooled directly in the greenhouse. They're virtually pure CO2. Doing this, you of course increase your efficiency of the combined heat and power, but you also feed the greenhouse with extra CO2 that the crop will capture, and that will help you to grow the crop quicker. The yield that we see is between 10 to 20%. So nonetheless, we capture the heat, we produce the power, but you can capture the CO2 out of the gas genset. So more value for our customers. Typically in greenhouse application, the power is sold to the grid here in West Europe. In Russia, however, the power is sent to the lights to light the greenhouse, and the CO2 and the heat is used to keep the greenhouse warm, of course. The most successful place where we have greenhouse application is Holland. Holland, we have 700 megawatt installed, extremely popular. We started that in early 80s. We have more than 500 catalysts installed to date, and 3,500 gas gensets have over 100,000 hours as we speak. Typical greenhouse in Holland, you can see here, 2 megawatt units producing 2.2 megawatt of heat, 1.5 ton of CO2 per hour, and the efficiency of the system is above 96%. That's a very good deal for the growers in the greenhouse. Here another one in Belgium. This is a combined system with 2 gensets, 3 gensets actually, at 4 megawatt total. And you see, I hope you see on the screen the lights that the genset is powering, and the heat is recovered, so is CO2. Another example for greenhouse, this one is in Siberia, and in that one, those who can read Russian can read on the bottom right corner, 3520 for us, 2 megawatt, heat recovery, and no CO2 in that one. So, a lot of heat, a lot of steam, fresh water, and CO2. What else can we do with the cogeneration? With the cogeneration, we can produce chill water. And to do that, we feed an absorption chiller. I don't want to go into details of the absorption chiller technology, but it's a machine that you feed with heat, and it gives you cold. So typically, the cold you can obtain with an absorption chiller is 45 F, 4 to 6 degrees C. And to do that, you have two technologies. Either you use the hot water or very hot water we can send to the absorption chiller, like in the chart here, or you can directly send the exhaust gas inside the absorption chiller. The hotter the media, the more efficient the absorption chiller. So that's why there is an advantage to use the exhaust gas directly. So in the chart here, you see a direct-fired absorption chiller, and you have production of cold water at 45 F and 6 degrees C. And also for the winter time, we have this 90 degrees C for heating. This was implemented in this airport in Tunisia, where we use the chilled water for the summertime and hot water for the winter time. Chillers are very popular in airports. Here is another one in Germany, in one of the major airports, 2 megawatt. 1.5 megawatt chiller, hot water for the summer, hot water for the winter, and chill water for the winter. Again, direct-fired absorption chillers you can see on the picture here. Absorption chillers not only for airports. Here is an industrial application that's been ongoing for over 10 years. It's a 31 megawatt cogen producing everything: hot water, steam, and absorption chiller. This is EMD, is a chip manufacturer based in Germany. So we can do hot water, steam, fresh water. We can do CO2. We can do chilled water. So what else can we do? The next application is to combine everything. In this quad generation, soda bottling bottlers, very popular soda brands, are using this technology to produce CO2 that they put in the drinks. Yeah, it's possible. Cooling for the factory needs, heating for the factory needs, and of course electricity. This is a popular application called quad application. Now, next time you drink a soda, you probably take care of what you drink. If you don't want to use the heat from our CHP system, what else can you do? And you can do more power. Most of you maybe are familiar with these combined cycles, and actually here it's almost a combined cycle. It's called an organic Rankine cycle. It's the way to use the heat that we recover from the CHP into a power generation system. In combined cycles, the media is usually water and steam. In ORCs, is actually a different fluid. That's why we call it with a different name. It's a thermal oil that is very special and will produce extra power from the CHP. Now I would like to touch base with you on different CHP systems that are used in a renewable environment. Maybe you didn't know that CHP are possible in landfill application and digester gas application or wastewater treatment plant. Actually, nonetheless, they're possible, but they're essential. In this example here, it's a landfill that uses CHP. Its example is from Aix-en-Provence, France, and in this 1 megawatt landfill application, the heat is used to produce hot water, and this hot water will actually dry the leachates. The leachates is the liquid that is remaining at the bottom of the landfill that has to be pumped, and prior to transport, they would raise the concentration of these leachates to reduce the transportation cost, and they use the free heat of the landfill genset here. Another one extremely popular and required combined heat and power are on the wastewater treatment plant. Wastewater treatment plant, they uses anaerobic digester to digest the wastewater waste. And here is an example in Jordan. 6 megawatt, where the heat of the genset will actually be fed to the digester, enhancing and quickening the digestion process of the wastewater treatment plant. More near our current application, this is an experience here, a project here in Canada, in Ontario. This is not a wastewater treatment plant. This is a modern digester where they use animal waste and to produce biogas, and this biogas is feeding a 1.6 megawatt genset, and the heat from that genset is actually sent back to the digester to enhance and quicken the digestion process. So you see a lot of different application in the natural gas world. We can do hot water, we can do hot air, we can do steam, and sometimes a lot of we can do fresh water, we can do cold water, we can do CO2, and if you don't need the heat, you can also produce a bit of more power. So as a conclusion to this presentation, I'd like to review and see that there is many different CHPs, and some are simple and some are complex. What is important for you to keep in mind is Caterpillar has proven expertise. Our CHP reference, we have CHP engineering capabilities, and our Caterpillar dealers around the world, those are near you, they have the product support expertise to serve your business. And as a takeaway, I'd like you to take that in mind. Cat is a CHP expert. Cat has proven global reference around the world. And I'm happy now to take questions, Nick, if this is the appropriate moment for questions.
Absolutely. And thanks, Francois. Nice job. I appreciate you taking the time to go through all the different applications that we see. I do have quite a few questions that I received here from the audience, and I'll go ahead and pose a few of these to you here. Our first one is, if I'm pronouncing your name right, Mihai Dogaru. He's a manager of studies and projects department in Romania, and he asks, how can we reach the new emissions limits of NOx, specifically 350 milligrams per normal meter cubed at 3% oxygen, for a Cat 3516A that it looks like currently has a higher emissions output than their new local regulation?
So the question is, can we reach 300 milligrams of NOx at 5% O2? Is that correct?
He states his question at 3% O2, but very close to that, yes.
All right. So the Caterpillar gensets, they have different ratings for emissions, and we publish usually two, one at 500 milligrams and one at 250 milligrams. And I know, for instance, the French regulation is already at 350 milligrams, and we have different settings for these, but this is relatively easy to achieve. So we just have a different programming and mapping, and we set the engine differently, the timing is set differently. Fuel consumption is impacted when you run at 350 compared to 500, about 1%.
Okay. Thanks, Francois. Another question I have, actually quite a few questions are coming in and asking about high temperature cooling options for Caterpillar equipment. Specifically, what Cat models, let's say besides the 3500 turbocharged after-cooled A-series that you had mentioned, offer high temperature cooling options?
Well, these are the 3500A series. We have a 500 kilowatt, 750 kilowatt, 1 megawatt, 1.5 megawatt, and 2 megawatt at high temperature. Depending on the country you operate, you would sometimes be able to run them with a jacket water at 127C. 127C is 260 F. In some other countries, they will limit the temperature to 110 C, which is 130 F.
Okay. I see here. I'm sorry. Go ahead, Francois. Sorry.
On all our biogas generator sets, the jacket water temperature is elevated to combat the aggression of sulfur and contaminants from the gas, and they all run with elevated jacket temperature at 110. So that's a good thing. It's not 127, but it's already 110. 110 C is, again, that's 230 F.
Good, thank you. Here's another question related to your discussion of greenhouses. Is it practical to use a G3412? And for those on the line maybe not familiar with our product ratings, that would be about a 350, 450 kW size electric genset. Is it practical to use a G3412 and an SCR to provide carbon dioxide for greenhouses? Does this make sense in a cost per kilowatt hour or cost per kilowatt basis?
Yeah, technically it's working. Probably the SCR will actually make it very clean and quick CO2. However, the economics of that might be a bit of a challenge. It's a bit small. Just the SCR will cost probably twice as much as the genset.
Okay. I also have a question coming in from Wissam Balshi of Cummins, asking, are there government incentives for CHP outside of the United States and outside of the European Union?
Actually, there is from time to time. The most popular are those in Europe and in some places in Asia, which are actually significant incentive. It's like good framework policies from the continental governments to favor high efficiency power generation or energy generation in general. I'm aware Southern Africa has a system in place to push for combined heat and power.
Okay, good. Thank you, Francois. Another question. We're getting plenty of questions here. What brands of steam boilers would CAT recommend? This is from Vasily Kiselev of Mantrak.
Yeah, well, we have various brand available. Actually, depending on the situation, you'll see manufacturers will have their advantages and their disadvantages. So, if you would want to have one steam generator per genset, because you want flexibility and availability, then you would normally go to a small 1 ton per hour type of a steam boiler. Then you will select this kind of manufacturer. I don't want to mention too many names on the line today. If you want to combine the power plant exhaust gases into one large steam generator, then we would use a different steam boiler manufacturer. I hope that answers the question.
Thanks, Francois. Another question that I saw came in that said, I thought I saw a 100% or over 100% efficiency number on a slide associated with your heat pumps. How is that possible?
Yeah, my best friend is Harry Potter. No, I'm joking. No, this is no magic here. I mean, the way efficiency is calculated is always calculated on the LHV, the low heat value of the gas. And you know there is two ways to look at the efficiency energy from the gas. You have the low heat value and the high heat value. And actually, the 108% is capturing this hidden part that you don't see in the low heat value. If you would calculate the efficiency on high heat value, of course, it will be below 100%. There is no magic.
Okay.
So in more details, the high heat value contains the water that is embedded in the methane, and the low heat value doesn't have that. It's about 10% difference of heat, the latent heat of water between LHV and HHV, and that's why we have this 108, because we can recover with the heat pump and the condensation. We can recover this latent heat I don't want to be too complex on the thermodynamics here, but it's 108% on LHV. That's correct number. It's good, no?
It sounds good. A question here from Mihai Dagaru from Dalkia in Romania. It was said at the end of the presentation, if we don't need heat, we can have more power. Is that correct, and how can this be achieved?
Yeah, that's the organic Rankine cycle. Maybe I can bring the slide back because it was not so far. The organic Rankine cycle is just like a combined cycle that is popular on turbines. Here it's performed with the total heat from the genset, the jacket water heat and the exhaust heat, and we actually boil off a fluid which is not water and turbine it into a turbine as a normal combined cycle would do. It's a Rankine cycle, except it's not water. It's an organic fluid or thermal oil. That's why it's called organic Rankine cycle. But you produce extra power by spinning a turbine, a steam turbine. But the steam is not steam. It's a vapor of that thermal oil.
Thank you, Francois. Another question coming in from Vince DeMarco with Washington Gas Energy. What is the typical installed cost per kilowatt for engines in the 2 to 5 electrical megawatt range for operation on natural gas?
With what type of heat recovery? I'll think hot water, for instance. Let's pick hot water. I would say $800 per kilowatt. I think that's a good number.
Okay.
That includes the genset plus the heat recovery system.
And another question, I see a couple people asking questions about the operation and maintenance cost. So if the installed cost is around that $800 per kilowatt, what can one expect for the operating and maintenance costs of a CHP system like the ones we're discussing today?
Well, they always, I'll give you a high number, but I know they're always below this. I brought that on one of the first slide. So typically the operation and maintenance cost are between 0.7 to 1.5 cent. This is the last line on the slide here. 0.7 to 1.5 cents of US dollar per kilowatt hour. That's typically what you should should calculate, and depending on what you want in your service, depending what insurance you want on your power, on availability, the price may differ. The quality of gas also differs. Makes difference.
Thanks.
Typically, a steam heat recovery costs a bit more to operate than hot water. Steam boilers, they need special water to go into. You need the water treatment and so on. So that's probably in the high end of the 1.5s. And hot water is more simple.
Good. We have a question from Mara Kamis from Mantrack. For the hot air application you discussed, is this needed for certain gas units or all? So in addition, what are the requirements, I guess, for the capture and use of hot air that would need to be provided?
Well, I'm not sure I understand the question right, Marwa, but what is important is you transform the heat from the genset, either the water, the hot water, or the exhaust gas into hot air. And if you do that, you can obtain a very hot air. And you probably don't want to enter safety hazard things. So you have a lot of precaution that needs to be taken in a tunnel. And you normally mix it with fresher air from the outside to produce large volume and control the temperature of that hot air. It could be done for one genset could have his own system, or you can combine multiple genset heat into a system that would produce that hot air. That's the one I would recommend.
Thanks, Francois. I have another question. I apologize, I lost track of the person submitted this question, but what temperature steam can I achieve with gas gensets?
Well, the exhaust gas of the Caterpillar gensets are between 460 and let's say 520, which is always below 1000 F. So you can't obtain steam more than that. So that probably gives an answer. So temperature of steam, typical temperature of steam we use on gensets is up to sometimes 15 bars, 10 bars, the typical number, and I think this is 280 degrees. So around 300 degrees Celsius for the steam. It's about 10, 15 bars. 300 degrees Celsius is 570 F.
I have a couple people, Francois, asking questions about lower temperature steam. So one specifically from Kevin Reinhardt of Omnova is, can I produce 200 F steam with, say, a 1.5 megawatt genset?
Yeah, and that's exactly, let me brought up the slide. That's exactly the slide I brought up earlier in the conference. It's the beauty of using our hot ebullient cooling gensets that have jacket water temperature at 127, and which is 260 F, and you can do a lot of steam at low pressure and then low temperature, and that's what is used very frequently in the food industry, but in other applications as well. And the beauty of this is a normal, if you would use a normal jacket water temperature genset around 90 degrees, you would be able to produce only 1 ton per hour of steam per megawatt electrical. And if you use that system, you can produce 60% more, 1.6 ton of steam per hour. So that's a very big difference. Keep that in mind. We can produce steam. I mean, it's a well-known fact that genset cannot produce a lot of steam compared to other equipment. Yes, that's still correct. But if you need steam, we can have some. Let's look at your temperatures and let's look at your pressures. Reinhardt is correct.
Thanks, Francois. I have another question here. This is from Jake Robinson of Toward Strategies. Is there opportunity to run natural gas from a stranded gas well to produce power to sell to the grid?
I'm not sure I understand. You said from natural gas?
Well, it looks like, I think he's asking about like a field gas, or he phrases it as a stranded gas well. Can you operate a natural gas genset on stranded gas and sell the power produced to the grid?
Stranded gas, I understand stranded gas as being gas directly coming out of the well. Is that correct? I think that's how I understand it. Answer is yes. There is Caterpillar is very famous on petroleum to operate on field gas or associated gas. There are many different names for these type of gas. They contain a lot of heavy hydrocarbons that might be required to remove or to separate before we feed the gas into the engine. But yes, Caterpillar gas genset can accommodate a wide variety of gas, including these gas.
Thanks, Francois. Question coming in here. What sort of problems do you see operating a combined heat and power system using biogas or landfill gas?
I see no problem. I actually encourage it. And this is actually the last 3 slides of the presentation. Let me bring up here again. Yes, if you have a chance near your landfill to have a heat consumer, that's fantastic because you can use the heat from the landfill gas or the biogas, and the heat produced by the landfill power plant or the biogas power plant, and send it to the local customer. Heat can be stored but cannot be easily transported, so you need to have a heat consumer nearby. The only thing, since you have contaminants in these gas, the only thing you need to pay attention of is how low you cool down the exhaust gas and what's your stainless in the exhaust gas heat exchanger. but this is quite easy to solve. This is not very difficult technical problems, and this one here, in France, they use the heat from the genset to dry the lithiates. This is a landfill, and every other anaerobic digester I know uses the heat from the genset.
Thanks, Francois. Good question coming in from Kip Doyle at ITG. He notes that in your exhaust application, you seem to go below condensation temperatures. How do you handle condensation in the exhaust system?
Condensation in the exhaust system is becoming popular and more popular, and what we want to capture here is the famous high heat value I discussed earlier. This is a 10% energy in your gas that you can capture if you condensate. So that's something we don't want to let it go. Now, this is right. When you condensate, when you cool down the exhaust gas to below dew point, you produces drops of water, and this water has to be addressed. Even on very clean natural gas, you cannot assume that there is zero sulfur in that gas. So you may find this water from the condensation, it could be acid. So depending on the local regulation, you may need to neutralize this water before you dispose of it on the environment. In the greenhouse applications, for instance, we condensate big time, and in Holland you cannot reject this into the atmosphere. So they neutralize it before they dispose of it, but they don't use it for irrigation.
Okay.
To neutralize, you can use lime. I know there are other things you could use. Depending on how big your plant is and how low you condensate, your volumes of water can differ quite much. So, yeah, this has to be addressed, and that's a good point. Yeah, good question.
And I think I'll do just two more questions, Francois, and I think we'll be close to the end of our session today. And I do apologize for those. We have quite a few questions coming in that I acknowledge we're not able to respond to today. So here's one from Manila Goka from Energy Choice Inc. If you use heat to produce more power, what would be the total electrical efficiency?
Slightly higher. In my example here, you could win. I think you could win up to 7%.
7, 8, 11.
In heat here, it was 7%. It was 110, 150 kilowatts here for 2 mega. Let me bring this slide again. ORCs, yeah, ORCs. Here we go. So the ORC is a very costly equipment just for 150 kilowatts. Here it is. But it's important. In some cases, you raise your efficiency by 7 points.
Okay. And this
in other cases, you can use it for. I've seen it in landfill applications. It's becoming more and more popular in landfill application too, where there is no heat need, and they want only power, and you can sell that power, and or there is regulation where you need to use all of your gas, and if you have extra gas, you don't want to flare it, so you insert it and burn that gas in a boiler that you insert in the ORC. So that's a typical trend. Thanks,
Francois. Okay, a question here. I think I may have lost track of the question asker. What is the typical reliability, availability of a gas genset? Well, in CHP applications, we have dealers and customer successfully reach agreement, and I know 98% is a number that is currently practical and contractually used here in West Europe. This requires a lot of expertise. This required a well set up product support and a good agreement with the customer. But 98%
is very practical. And this is for cogen in West Europe. But keep in mind, I know we have Mantrack people here on the line. They have installed 18 megawatt power plant in nowhere, Tanzania, at the border of Mozambique. It's a quite remote place called Matwara, a very nice place. And this 18 megawatt gas-fired power plant was installed 2 or 3 years ago and reaches today 97% availability, which is a fantastic, really, really good number. Congratulations to Mantrack.
Thanks, Francois. Maybe I'll sneak one more in because we do have another couple minutes left. But from Franco Gasparini of Foster Wheeler, what is the minimum required gas pressure for a CHP system?
I'm not sure I understand gas pressure. Was it pressure?
The gas pressure required.
Sorry, pressure. The audio didn't get through. Oh, gas pressure. So gas genset from Caterpillar can take pressure at 100 millibars. So that's typical what we need to have at the engine. So before that, we normally have what we call a gas treat. It's a pressure regulator and safety valves, sometimes even a meter. These could take a bit of a pressure drop. Then I recommend that the feeder to the power plant is either minimum 200 millibars. That would be nice. 1 bar is fantastic, but it's low pressure. That's the beauty of our lean burn low pressure gensets. We also have in our range high pressure gensets when available. We don't know. We have both technology. But lean burn is nice with low pressure because you can actually install these cogen power plant, this CHP power plant, downstream and remote from the gas grid. Imagine you're far away from a gas distribution pipe, so your gas utility will deliver gas only at quite low pressure. That would require, for a turbine, for instance, a compressor. For us, we don't need any compressor. We can live with 200 millibars and 100 millibars at the engine.
Thanks, Francois. And with that, I would like to ask our audience, a lot of you stayed around, and I appreciate you doing that and participating with us today. Before we conclude and let you go, I have a couple questions. I'd like your feedback. Were you previously aware that Caterpillar was a global provider of gas-fueled cogeneration solutions? Please do go ahead and take the time and let us know your thoughts on this question. And yes. Once you do get a chance to submit your answer, please do click Submit Answer there. We appreciate that. And then secondly, how would you rate the information provided to you today on a sort of a scale from high to low? Please let us know what you thought about the information. Hopefully you learned something today. I actually think I did. Thanks, Francois. And
my pleasure.
We appreciate it. This will conclude our webcast today. Combined heat and power with reciprocating engine generators, cost-effective and clean energy. Please do check back in with us. We will be providing additional webcasts early next year, targeting one on low energy and biogas in the February timeframe. We'll be sure to post the details on our news feed, which you do have a link to on this console. We look forward to seeing you again soon. Thanks much, and thanks, Francois.
Welcome. Thanks. Good evening and good day for everyone.